Thanks for staying here. One last thing. We originally thought that we were done with the authentication thing. I have to make additions to that. I asked how we would find out the IP address of the management module that we're going to impersonate. First of all, the thing that we describe here is just what we do. Even if we don't send IP addresses, we will be sent IP addresses. So the module will send us its IP addresses. So we know in which networks it is in, and well, the probability that it's managed from one of these networks is quite high. And what we normally do is we just scan. We scan for the management console. We just send different IP addresses on each try, and it will refuse to authenticate if it doesn't know us, if it doesn't know our IP address, and it will say, no, I don't know you, go away. So in this way we can actually scan for the IP address of the management module. The other thing is that with Checkpoint Firewall 1 4.1, you don't need any more an encryption license to use FWA1, and FWA1 is the standard. So SKey and FWN1, it's almost a bit obsolete if you have version 4.1 of Firewall 1. So this defaults to FWA1, but still FWA1, as we have seen, is significantly broken. And what we have tried in the past is just to send, without knowing the encryption key, just to send 0 bytes and hope that it gets decrypted to something sensible, because the encryption key is, well, hopefully it's distributed. I don't know the English word for that. Anyway, but each key is normally, it's hopefully as likely as each other key, so it's evenly distributed. That's what I was looking for. And we just hope that we would hit a key that would decrypt 0 bytes into something sensible. We had it run one night, but it didn't turn out to work. So you still have a very, very slight chance of succeeding. But actually, what you have to transmit is at least 7 bytes, I think. And well, getting those 7 bytes decrypted to the right thing is pretty unlikely. So, but back to the intermodule protocol thing. We said before that IP addresses. That you transmit your own IP addresses in this protocol. So this opens a pretty obvious thing that we didn't talk about at all, because you can switch authentication off for certain IP addresses. So many people do so by editing the control.map file and switching authentication off for 127.0.0.1, because they assume that these connections can only come from localhost. But like we said before, hey, it's not that the IP source address that counts, it's the IP addresses that we send. So if anybody switches off authentication for 127.0.0.1, then we just send 127.0.0.1 and we can get into the whole thing without authentication. And this is one last thing that I want to show with the intermodule authentication. It's actually, the switching off is actually recommended by a website. And yeah, because you lose a lot of trouble. You get around a lot of trouble doing that. You don't have to configure keys and stuff and everything. And well, it's not recommended by Checkpoint. Just let me make that clear. It's recommended by another website. I will not tell you. just do a search in the search engine for that. That is the line here. This is the line that I've inserted. Those rules are parsed on a first match basis, so they go from here to there, and then finally this one will say */none for 127.0.0.1. For nothing, for no command, authentication is necessary. And of course we have a tool for that doesn't authenticate at all. We can run this attack. So if I'm not mistaken, we should be able to do it right now. It's back there. So just a second, I have to put that microphone away. Okay, again we are attacking the firewall here. So let me just restart the firewall to make sure that this has really been honored, the changes that I've made. FW stop, semicolon, FW start. Stop it started. Okay, and let's see whether the security, it's the correct security policy that we have loaded. Okay, it comes up again. Okay, we can't ping it, as you see over there. So now we use our FW1 none authentication. tool. As you see, it takes just the firewall's address, which is 194.221.6.159. This is the IP440, and we say we are coming from 001. We don't even have to do IP spoofing or whatever. We just go like that. It authenticates, authentication method none. As you see up here, authentication method none. We don't even have to authenticate. We say we are 127.0.0.1. We just send the unload command again, and as you will see, we will be able to ping the firewall again or do worse things, locally exploit everything and own the complete firewall. So that's like that. There you go. So never ever do that. So this was a little addendum, and now we can really go on to the firewall filtering mechanism. So I will just be giving a short overview of the filtering mechanism, and then my colleagues will take over and I will be done. I'll just give you a short overview, and then we will have quite a lot of demonstrations that will show to you in which way we can subvert the filtering mechanism itself. So this is what Firewall 1 works like. There's a packet in the uppermost corner, in the left-hand corner. The first thing a Firewall 1 does is it checks whether the packet is a fragment that has either a non-zero offset or the more fragments flag set in the first fragment, and it creates a chain of fragments. This is called virtual defragmentation. So it makes sure that the integrity of the fragments, that the fragments have integrity, and that they don't overlap and stuff like that. They have integrity checking, and after that, if all fragments are collected, it is passed into the inspection engine. The inspection engine does the following. It has a pre-inspection part. The pre-inspection part is in the loadable kernel module. It's native code. It does the following. It looks at the fragments and then looks at a database, at a table. It's the connections table. And if the whole packet belongs to a connection that is already in the connections table, well, at the beginning it's empty, but later there will be connections added to the connections table. How this works we will see down here. But let's assume there's an existing TCP connection, and if the packet belongs to an existing connection, then the pre-inspection part will see that it's in the connections table and will accept the packet. The pre-inspection part, apart from that, make sure that, because Firewall 1 basically looks at the first fragment of this chain of fragments. It only looks at the first fragment because that's where the interesting information is, like the IP header, the TCP header, and the UDP header and ICMP header. And it makes sure, for example, that the whole header is contained in the first fragment, so that we can't play those old fragmentation tricks like fragmenting the TCP header and stuff. So this is all done in pre-inspection. If pre-inspection does not accept the packet, then the whole packet, or the chain of fragments here, is passed to the virtual machine. And the virtual machine executes the inspect code that has been generated from the rule base. So you have a rule base. From the rule base, inspect code is generated, inspect code is compiled. It's a RISC-like assembly. It's a RISC-like machine code that you have, and this is executed by the virtual machine. And the virtual machine basically represents the rule base, and if the chain of fragments meets the rule base, then a corresponding entry is made in the connections table. So this is the simple case. We have more complicated cases like the FTP protocol, for example. The FTP protocol has like control connections and corresponding data connections. Whenever you download something, a data connection is opened, and you don't have rules in your rule base for those data connections. You just have a rule that allows outgoing FTP, for example. The secondary connections, like the FTP data connections, are handled using a so-called pending table. So the Firewall 1 monitors all the connections that are in the connections table, monitors especially like FTP control connections, and whenever it sees a port command, for example, or a passive command, depending whether you do active or passive FTP, it will make a corresponding entry in the pending table, and the pending table means that the firewall is ready to accept the connection, and as soon as the connection is accepted, as soon as the data connection arrives, it will be put into the connections table. So only, of course, if the packet meets the rule base. So that's why after the virtual machine, either the packet is accepted and the corresponding connection is put into the rule base, or the packet is rejected. So this is how the whole thing works. And we have some other things. For example, if you're using IPsec networks, then before the pre-inspection part, there will be the decapsulation and decryption. What we will be using is the proprietary form of encapsulation, the checkpoint proprietary FWZ encapsulation. This is done also right before pre-inspection, but we will hear more about that later. So, I was talking about connections. UDP. UDP does not have connections, but they use virtual connections there. So if you have an internal client and an external server, the internal client sends a request to the external server. Then we have from a client port C an accepted UDP packet to a server port S, for example. The rule base accepts it, and also for UDP connections, there will be connection entries. So the interesting thing about that is that UDP replies are accepted for these connections. That's the little tick mark that you have in the policy properties. And yeah, normally you have to tick this, because otherwise you would have to open all ports from 1024 up for incoming replies, for potential replies. That's why you normally want UDP replies to be accepted, so you don't have to open the ports. And these UDP replies are accepted from any port, from any server port. This is not a security risk itself, but it makes things easier later when we attack this. So what was I saying? Yeah, it was about we have virtual connections for that, and yeah, we have a connection from a client from port C to a server port S, or a wildcard port, the any port in the other direction. So let me quickly show you how a connection table entry looks like. It's source address source port, destination address destination port, and protocol, those 5 parameters that uniquely identify a connection in the internet. So let me quickly go through an example of stateful inspection. The FTP protocol, the upper part is the active part, the lower part is it's the active case, and down there is the passive case. The active case is the FTP client connects to a server from a non-privileged port to port 21 of the server, and this is put into the connections table. The connections table is being monitored, and when firewall 1 sees a packet that contains a port command, that is the beginning of the packet, has PORT, and after that the port information, then it is parsed, and a corresponding entry is made into the pending table. And as soon as the data connection is seen by the firewall, it would look at the pending table and see, wow, there's a data connection, and it matches the data connection that's in the pending table, and this will be moved to the connections table. So the same thing is true for the passive case. You have a passive connection, the client sends PASV. PASV is ignored by the firewall, but if the firewall sees a 227 reply, that's the normal reply to a passive command, if the firewall sees a packet that begins with 227 space, then it's, and which is coming from port 21, then it thinks that this is a passive reply and will make a corresponding entry into the pending table, again this time from the client to the server, because in the passive case the data connections and the control connections and the data connections are from client to server, and then as soon as it sees the connection from the client to the server, here it's the port is 436, which is 4 times 256 plus 36, which is 1060, and it will accept this data connection. So this is how stateful inspection works with the connection table and the pending table, and my colleagues will now, I think, fill in the details. What's the next slide? Exactly. So it's now up to my colleagues.
Fix the firewall.
So the next exploit we'll be looking at is an exploit of the fast mode service. Fast mode basically allows a connection based only on whether or not the source or the desk port match the fast mode service. For example, you may enable fast mode for HTTP if you wanted to make the processing load on your firewall for web traffic a lot faster. The problem with this is that it's pretty trivially looted, and one of the ways in which we can leverage this to our own ends is to do stealth scanning with a source port set to port 80. Yeah, go ahead.
Okay, I need a little bit of time to get the firewall to a reasonable state. Alright, now a lot of what we're showing depends on misconfiguration. So we don't have anything up our sleeves. I'm going to show you exactly, we'll start with the default, we'll show you all the changes we make. So let's see. We have the IP440 network object, and spoofing protection is currently applied correctly. So let's see. So we have the Solaris box. Anyone can FTP or HTTP to it, and the Solaris box is allowed to FTP out. Everything else is denied. Go on properties. Let's kill all this. So this is basically a default install of Checkpoint 2000. Just a straight sense game. Just 100. Just not sure what things are. 170, 16, 14.
So over on the attacking box, we're just doing a simple SYN port scan, just to demonstrate that, in fact, the firewall is working as it should.
Okay, so what we're going to do now is make HTTP a fast mode service. And it says here that if it's a fast mode service, you can't do encryption, address translation, or accounting for the service. Okay.
So if we redo the port scan that we just did as a fin scan with a source port of 80, which is the fast mode service, we should see a lot more. And in fact, we see everything on the Solaris.
Keep in mind you can't get to any of these, so it's not that big a deal, but it does let you just scan behind the firewall.
Show the next slide. The next up we have port parsing. This is an example of the end-to-end ambiguity that some passive monitoring devices are susceptible to. In this case, the firewall gets desynced from what's actually being implemented by the end host FTP server. Hi. So the command being sent in the port command, the arguments to it are the IP address and the port to connect to, split up into octets, comma separated. What we do is we can leverage a difference in the way that our end host FTP server interprets this command versus what the firewall believes is being stated here. By using a number here for the port, or for the end of the IP that's larger than what can be represented in octet. So for instance, on the left-hand side, we have the actual machine, which believes this string evaluates to the IP address 172.16.0.2, while the firewall believes that it's 172.16.1.2 because of the carry. So how can we actually use this to our own ends? A good application is to use it in a bounce attack. there are not too many FTP servers actually that are susceptible to bounce attacks anymore, but as it turns out, the Solaris FTPD still is, and so we can use this, for example, to exploit a hole in an RPC service. So, John, do you want to set it up?
So let's see. So, well, hold on. Let me make sure I cleaned up.
So what we have running is a Solaris FTP server, the firewall, and an attack box. What we're trying to do is actually run an RPC exploit against this Solaris server, but of course all the high-NERD ports are closed. So what we do is we make use of the existing FTP channel to perform a bounce attack to cause the server to send an exploit against itself, essentially.
So you see here that there's a public directory that we can write to, and that's what we're going to use in this attack. We're going to go ahead and upload 2 files, which we're going to send to the ToolTalk database daemon. Standard exploit. Crap. Control H. Control U. All right. I'll find it. There we go. Okay. Okay, so what we want to do for our attack is this. We want to say connect back to 170. We want to tell it to connect back to itself on. We happen to know that the port we want is 32775, which is where TTDB is. You can actually scan for that by binding. So that's what we want to do. You can see the firewall doesn't want us to do that. The firewall says, more or less, wants to enforce that the data connection is going back to the FTP client. So we're going to use the ambiguity here to trick it. In earlier versions of Firewall 1, there's other easy ways to trick it, but because of the recent passfeed bug, they kind of tightened down on how it parses the FTP protocol. So this actually works out pretty nicely. So, and again, we just threw this to demo. We were supposed to have the video out on here, so it might not work, but we'll see what happens. See that the firewall let us get away with that because what it thinks is that we're connecting to 192.168.0.2, and we're really, and the FTP daemon sees its own IP address 172.16.0.2. So then we'll retrieve a file that'll kill the ToolTalk database daemon. If anyone's ever used the exploit, use -K flag. Now, one obvious problem here is that you have a socket coming from port 20 to 32775, and that's going to take like 4 minutes or 5 minutes to time out. So we did some NDDs on the Solaris box to make it time out quicker. So actually I should show real quick the payload of what we're doing. Now in order for us to get anything back, I'm just going to make it easy. I'm going to send an extern back. But I'll do it in kind of a way that we've used with a bunch of Firewall 1s. So I'm going to go in to the policy settings, and I'm going to accept domain name over UDP and over TCP, which you know in Firewall version 4 is the default configuration. A lot of the attacks we're showing will depend on this, but so now there's basically an implicit rule that anyone can connect anywhere on port 53. So what we're going to do is have it send an exterm over port 53, which is pretty easy to do.
Sorry.
this is the payload of what we're doing, and you see that we send to display 59589. And what happens is that wraps around, well, your display number is added to 6000 to determine the port, and that wraps around 65536 to hit 53. So it'll make a TCP connection out on port 53.
Show that on a TV?
Yeah, so on the Linux box, we have a really simple proxy. See right here, domain. We're just doing a netcat to the box you're looking at, the O3 box, port 6000. So in theory, this will work.
Boom.
Okay, go away. Okay, but I mean, you're running a remote buffer overflow, so if you want to get fancy, you can send there's certain things that are allowed through Firewall 1 by default, even on 4.1, like RDP packets. So there's definitely some channels for communication there.
The next exploit in the FTP server, in the FTP proxy that we're exploiting is a well-known one. It was discussed at length on BugTrack, and it has to do with the way that the firewall verifies the pass-v command, actually as well as the port command. And what it actually does is it looks at the discrete TCP data within IP packets instead of reassembling the entire TCP stream. What this opens you up to is a sort of a framing attack where you can actually leverage the error messages sent back from the server to sort of fake out the firewall into believing that a real pass-v positive response was sent back. And so the way we do this is we advertise a small MSS in our outgoing connection to the FTP server, so that when the FTP server replies, its carefully formatted bounce message is split up like such. You have the 500 invalid command given string, after which the actual command that you sent is quoted, but it's actually sent in a separate discrete IP packet. And this tricks the firewall into believing that this pass-v command was in fact sent by the FTP server, and it opens up a hole. It opens up a hole in the firewall to allow that connection coming back. There is a restriction on this, though. Checkpoint by default restricts incoming data connections to high number ports. As it turned out, this bug was also existent in Cisco PICs, and let you open up a hole on any port, which is much worse. But anyhow, we can demonstrate that as well right now.
So we'll use the tool FTP Ozone written by Doug to open up the port. And note here that it was open. So we'll then send, and we're using the same files as before. Yeah. We'll open the port again. And then there's our term.
What's that? The next set of constraints that we look at are these one-way connections. Firewall 1 tries to restrict the data flow of a connection, for instance, for FTP data connections, by looking at the TCP header in the IP packet being sent, and checking the IP packet and seeing whether there's any TCP data in it. The problem there is that you can actually fragment your packets coming back, so that the TCP header and the TCP payload are in separate packets, which lets you establish a duplex connection. An example of this is in the original exploit that we had with FTP Ozone, you could only open up a one-way connection, but we found that the firewall responded very well to reopening the connection. Firewall 1 doesn't actually track sequence numbers, so packets that have the correct IP and source port, dust IP and dust port, will actually get associated with that connection as long as it's in the state table. So the way to bypass this one-way restriction is simply to reopen the connection, and then the firewall looks at what direction the first data packet coming back is in. In this case, the retransmission happens coming back to us. We can demonstrate that as well.
Okay, my extreme won't go away. Yeah, the fragmentation worked in version 4, but they fixed it in 4.1. So in version 4, you can just fragment your packets and get past the one-way restriction. But here, it's kind of a pain in the ass. So what I'm going to do is hook up the Spark, and I'm going to set up a netcat on there so we can see the data going both ways. Where's the...
Oh, yeah, that's it right there. Got it.
Okay. Can't see it. Well, I can't see what I'm doing, but pick 40. Where am I? 1, 2, 3, 4, 5. Okay, so we got that listening there. I'm going to use FTP Ozone to open up a hole. And then we can connect there. Right. Oh, it's broken. Okay. Take it before. Is it 5, 4, 3, 2, 1? Okay. Who knows what's listening there? It's one of my experimentation boxes. Okay, so data can go in this direction. Okay, so now if I go and type a response, it's gonna erase the connection from the connections table, so because it's marked as a one-way connection. So before I do that, I'm gonna prepare to open it back up again because we end up having to wait for retransmissions, and that takes a while. So is this on? Oops. What have I done here? Okay.
What John's doing here is discovering the ephemeral source port that we're used for this data connection, so we can use the same one when we make the second connection.
So I'm just going to use this I have to open the connection with FTP Ozone and then spoof a SYN in order to get the connection back into the table, and then when the Solaris box retransmits, then it'll get through. So. Oh, wait. Okay, so we see here's the connection. I'm going to come over on the Spark and type something. Then we see that it didn't come through, and now anything I type here won't make it across either. So what we can do is open the hole back up. Spoof a SYN, and then type some more. So you can see that now the connection's established in the other direction. So if we want to send data back the other way, we have to go through the process again. But you could probably script this with no problem and have a really slow two-way connection bypassing their mechanism. Okay. So this is interesting. What this is FWZ encapsulation. It's what they use for the Secu Remote. That's what they used to use for Secu Remote clients. What is the really lightweight tunneling protocol, and we're going to use that in a lot of our attacks. The interesting thing about this is you can send packets to a firewall 1, almost any version we've seen from 3.0 to 4.1, and in this IP protocol 94, and the firewall 1 will decapsulate it, and you don't need to authenticate, and you don't have to encrypt your packets or anything. So basically, the impact of this is you can send packets that you wouldn't normally be able to route to the firewall, which is fun. So it's pretty simple. What you do is you take your normal IP packet and you destine it to the firewall, and you set it to IP protocol 94, and then you append the real information to the end of it. So if you want to send it to like 10.0.0.1, you append that IP address to the end of the packet, and then you append the real protocol that you want. So it's just 5 bytes you stick on the end of the packet. Now it's not that simple. They obfuscate it a little. They do an exclusive OR with a value based off of the IP ID. So it's just a simple little trick to obfuscate it. What we do in all our tools is just set the IP ID to 1, and then we know the value, so we just XOR it with that. So, okay. What's that? Yeah, you can't switch it off. We'll talk more about that, but it's not in the GUI or anything. So what we have here is the general form of the attacks I'm going to talk about first are based on spoofing protection not being correctly applied. So if spoofing protection, if the firewall is misconfigured such that spoofing protection isn't applied right, then you can have a field day with it. So assuming that there's some rules that allow you to do what you want. So for instance, here our attacker would be 131.159.1.1, and what we're going to do is we're going to send a packet from something in the DMZ or internet to us by using this encapsulation, and that'll allow us to put data in it for it to inspect or to respond to it. You'll see the general form of the attack later. So basically, looking here in the IP header, you see the source address is a 10.0.0.1. So it's an internet or DMZ box. The destination address is, now the top part's the real IP header. The destination address is the external interface of the firewall, and then the stuff we append is our IP address. So what's going to happen is this packet's going to make it to the firewall because the destination address is the external firewall interface. Then it's going to get decapsulated. Then spoofing protection is going to check it, and if it's improperly configured, then it's going to pass it into the machine. So as far as the firewall knows, the packet came from the DMZ or the internet and is headed for our machine. So I can give a quick demo of this real quick. All I'm going to do now is just send a packet that meets the ACL just to show you that the encapsulation works. Now I'm using a tool called TUN that we put together, and this takes the protocol, so I'm going to do TCP, the firewall interface, then the source address, which will be our machine, The destination address is going to be the Spark. Destination port, we'll do 80, TTL 100. We'll make it a SYN. Now, let me bring up a TCP dump here. Oh yeah, we changed our demo a little. Let's see. All right. Okay. So what you see here is that we had an IP protocol 94 packet go through from us to the external firewall interface, and then now it's a legitimate packet, we just tunneled it, so the Spark responds with a SYN ACK because it got decapsulated, and then our box shoots back an RST. So you can see that that's just proof that the encapsulation works. So moving on to, we'll actually do an attack now. Whoops. So I'm going to break the firewall intentionally to show you. I'm going to make a mistake in configuring the spoofing protection. I'm going to forget to have entered interfaces in on the network object. This is just, we've seen this before. The other mistake, obviously, is to say any address from the internet interface, but it warns you when you do that. But when you do this, it doesn't warn you. So since it doesn't know what interfaces the firewall has, it doesn't know that we didn't correctly configure spoofing protection. Yet everything else still works. So it didn't warn us that we didn't do it. So now what we're going to do is spoof a port command from the Spark to us. So just to give an overview, we're sending a packet encapsulated from the Spark to us that contains the port command 172.16.02.128.7. So what the firewall thinks is that we're a machine on the internet FTPing to a box on the internet and saying, hey, connect back to me on this port. It's giving a port command. So the firewall is going to open up that hole. I'm putting a comma at the end for the new line checking. Gets around it. What am I doing here? Sorry, I'm a bit disoriented. So, options. So we're spoofing the packet from the firewall, port 1024, or excuse me, from the Spark to us on port 21. It'll be an ACK, or TTL of 100, it'll be an ACK. And I'm in the wrong directory. Okay, so in theory, we can now make an FTP data connection back through the firewall. And it let us do it. So, okay. So again, these are dependent on spoofing protection not being set up right. There's a couple things you can do if spoofing protection is set up. We'll get into that later. And we've run into a surprising number of people that haven't set it up, even though it warns you when you say install. Okay. Now this RSH error connections, it's really it represents another way another thing you could spoof to try to open up a connection back. We actually had another attack based on this, based on a collision in its use of the pending table, but we tested it like a couple months ago, and then we installed the latest version, and it doesn't work on the latest version. So we don't want to come out and say it worked at all, because we didn't really have time to install the old version. So we're not sure if this attack is valid or not. It almost works on the latest version. It adds an entry to the connection table, but the flags are wrong. So I'm probably just going to go past this. Well, I can cover it real quick. What happens is when it sees a RSH connection, it records the sequence number of the packet in the pending table, because what it wants to do is it wants to look at the first packet of the RSH connection to extract the error port information. So what happens is it uses the same table twice. It pulls out the sequence number and stores it in the table, and then when the next packet comes through, it pulls out the port number, stores that in the table, and then stores the protocol in the table. And then when it sees the actual RSH error connection, it matches up with that information. Now, there's a problem here because it's using the same table twice for two different things in basically the same way. So our attack is we send a TCP SYN with a sequence number of 5. Now that gets stored in there as a sequence number as 6, which happens to match up with this criteria for the second check. So it actually, our source port is the one that we can get to with the error connection. We're not sure that it works, so take that for what it's worth. But in general, when you consider if spoofing protection is open, then there's probably all the protocols that can get through a firewall 1, probably a lot of them can be abused for opening up back channels and things like that. So this is the one that we've had the most fun with, because it's a default rule in the Firewall 1 version 4 to allow UDP port 53 everywhere. So if spoofing protection isn't set up, what we've been doing is spoofing DNS packets from the intranet or DMZ to us, and then we can respond to them on whatever source port they came from. So in this case, we spoof a packet from 161 to us on port 53, and then we can respond to the SNMP daemon on the intranet or in the DMZ. So we can demonstrate this. Okay. Now I have a Solaris exploit for 2.6 SNMPD, so that's what I'll show. It doesn't always work real well, but we'll see what happens. So you see we're spoofing a packet from 161 on the Spark to us, port 53, the UDP packet. Now if you notice, oops, wrong IP, not the firewall, us. So we can leverage that for root. Maybe. So I got to open up a port, another UDP port, so I can talk to directly to the MIB process, not the relay. Oops. I messed it up. There we go. Now the thing that's really cool about this is that you can reach internal addresses on any firewall 1, and if there's any rules that let you talk to it, like any source rule or anything that lets you talk to them, then you can address the intranet. So for instance, in version 4.0 with the default install, you can talk to any DNS server on the intranet or DMZ. So, because you can address, using the encapsulation, you can address 10.0.0. whatever, or whatever you want. So that's a really pertinent application of the universal decapsulation. So I'm going to set up anti-spoofing protection now. Oops, I don't know what I'm doing. So I'll go in and I'll set up this net protection on the two, what represents our DMZ interfaces. And then on here, I'll set up others protection. So what that means is that any packets coming into our internet interface that purport to be from any of the other interfaces on the firewall will be rejected. Now, this opens up a small problem because this doesn't protect the external interface of the firewall. So in some of the versions of the firewall we've seen, if it sees a packet that has the IP address of one of its interfaces, it drops it immediately. But actually in this version we just installed, it doesn't do that. So we can send packets that purport to be from the external interface of the firewall, even though spoofing protection is fully applied. So then what you would need to exploit this is some sort of rule that allows traffic out from the firewall to the internet. So we have that default DNS rule. So what we can do is access the SNMP daemon on the firewall. Now, I talked to someone from Checkpoint, and in Service Pack 2, this is the automatic interface protection is set, so it's something worth checking. So we're basically doing the same attack, except we're using the external firewall interface. I should probably install a policy. And that's our IP 440. You can't do that normally. Okay, so the next thing we can do against anti-spoofing protection, that even if everything is applied, we still can leverage something, is we send something from, what we do is we spoof a packet from the from the multicast address or the subnet broadcast address to us. That if there's a rule that will allow it, then that'll get added to the connections table, and we can respond to that, and it'll get delivered to the firewall. So we essentially enable us to respond to 224.0.0.1, and that gets delivered to the firewall itself, to the UDP services listening on it. So in order to do this, it requires a little bit of a setup. We're going to run frag router over here so that we can so that I can use SNMP walk and have it SNMP. Essentially, it's going to be SNMP walking 224.0.0.1, but on the firewall. Okay, so we're running frag router on the second box here. We can look at the code real quick. So here's something we threw together that does FWZ encapsulation in frag router. Okay, so MISC FWZ. Now the only thing I really want to show you here is that if it receives packets destined to 2222, it rewrites them to the multicast address. So it's just a quick hack. So like I said before, we're gonna, okay. We're going to send a packet from the multicast address. Sorry, UDP. To us. So you can see that we're actually delivering packets to 224.0.0.1 on the firewall, and the responses are coming back. Now the responses come back from the actual interface of the firewall. So what we did to allow the responses to come back is the source port of our SNMP walk is 53. So the responses are destined to us on port 53, and therefore they're allowed through the rule base. So what you're basically here, you see an attack that works with spoofing protection fully enabled as long as there's a rule that allows you to utilize it.
Okay. So these were the layer 3 attacks and layer 4 attacks that we mounted against firewall 1. So what you saw is that's quite possible if you don't have spoofing protection to modify the rule base, not the rule base, but the state of the firewall in a way that allows you to get packets through it that you shouldn't be able to get through. So many people don't have anti-spoofing configured because they say, yeah, we don't have our services running, so we don't need anti-spoofing. But as you can see, anti-spoofing is also pivotal to the integrity of the internal state of the firewall. That is why you definitely should configure anti-spoofing. So, what else can you do to harden your Firewall 1 installation? Okay, the first thing mainly applies to Firewall 1 version 4.0. As we said before, this is what we have been doing experiments with for quite a while. Disable the implicit rules that allow DNS from any to any, because like you saw, you can, if you don't have anti-spoofing configured, you can spoof packets coming from DNS packets coming from the intranet, and then send replies to the intranet and basically access any arbitrary port on any machine, or UDP port on any arbitrary machine in the intranet, even if it's network address translator, because you can encapsulate packets. That's what we saw before. Disable this. Then the Firewall 1 control connections thing is also in Firewall 1 4.0 was basically an allow any to port 256, which is, as we have seen before, also quite dangerous, especially if you don't have an encryption license on that machine. So the last thing is ICMP, which is normally also enabled on 4.0 machines, also enabled from any to any. You don't want to have this. You want to configure this more restrictively. So this is the next point. You want restrictive access rules. No any sources or destinations. You don't want especially any sources. You don't want basically to you don't want to allow DNS from any to anybody, because if somebody else is able to spoof packets, then these packets will be parsed, and the internal state will be changed according to the packets, no matter which IP address that comes from. So this, for example, if the anti-spoofing for the firewall interface is not configured and doesn't work, as in our case, then you would be able to spoof packets from the firewall because you have an any source. Any destinations is I don't know whether what was the idea behind any destinations? I don't remember either. Perhaps let's get back to that, to the destination thing. That was something. I can't currently think of it. So you want to, then one of the first rules might be you want to deny broadcast and multicast. Oh yeah, the any destinations. If you go to the internet and say any, then this means that you also have outgoing packets, especially to the broadcast addresses, or to the multicast address that we saw before. So you can get reply packets back in to the multicast address, which is something you don't want. This was the idea behind the destination addresses, I think. Yeah, that was it. Then you want to deny broadcast and multicast addresses in your rule base. You can do that. And basically what you should do is have a rule base that adheres to the minimal privilege principle. So you want to get the rules as restrictive as possible. For example, when you want to allow traffic to outside networks, then you should just form a group of all your internal networks and then say not these networks instead of saying any on the outside. So you could, in addition to that, you could put into this group, you could put the more multicast addresses, 224 class D and E networks, 224 and higher, class D and E, like I said. You could put that into the group also and then say not, and in this way you will be, those spoofing attacks will not work anymore. So you should probably configure the anti-spoofing mechanism. That means that, yeah, you go through all the interfaces and tell the firewall which networks these interfaces are hooked up to and which IP addresses it may accept from these networks and which interfaces it mustn't accept. Then you might want to filter protocol 94 at your border router if you're not using secure remote, or if you're using secure remote with IPsec. This can, for example, also be done using IP filter. There was a posting on the internet. Where was it? The posting? Was it bug? It wasn't bug trick, was it? They do it with IP filter. They have a Solaris box and they have Firewall 1 on it, and they use IP filter. And Darren Reed said, has now a signature that says IP filter protecting Firewall 1 from the internet. It's a bit mean, but the protocol 94 thing is really something that you should block at your border router if you're not using secure remote. I think that Darren Reed signature was due to the fragmentation thing that happened to Firewall 1. Yeah, what is interesting to other denial of service attacks, by the way, that have been happening to Firewall 1. These attacks are based on logging. So as we saw before, you have the pre-inspect before it's passed to the virtual machine, and the virtual machine thing, it logs to the log server. But the pre-inspect code, mainly, most of the things in there, the integrity checks are logged locally to the local syslog. So if you have a lot of logs, then you get the load of the firewall quite high, and you will have a denial of service condition. And all these denial of service attacks, the fragmentation thing, and then there was an IP spoofing thing that also was could lead to denial of service conditions. Both of these were exactly related to this logging thing. So you generate syslog messages, and in this way, since the rate is not restricted, you get a very high load on the firewall, and your firewall doesn't accept packets anymore. So these are the hardening things. The first slide at least. We have a second slide on hardening Firewall 1. One nice idea that you might want to implement is that if you have a DMZ, for example, a DMZ, with different servers, with a web server, with an FTP server, we have shown that with the FTP protocol, it might be able to, an attacker might be able to open up ports that he normally doesn't have access to. But the ports are only opened for the IP address that the server resides on. So imagine a world or a DMZ in which every service is bound to a different IP address. That's what we do in our DMZ. We have like an FTP server and a web server, and the web server is bound to IP address 1, and the FTP server is bound to IP address 2. And nothing but the web server is bound to IP address 1, and nothing but the web server is bound to IP address 2. So let people open ports. There's nothing to find there. So you might be you might want to implement this. Just configure virtual interfaces and bind only the FTP server to a certain address and nothing else, for example. That might be a nice idea which can be implemented without going through too much efforts. And the other thing is you want to restrict control connections. Of course, you want to use FWA1 authentication, which by now with 4.1 is the default, and you don't need an encryption license anymore. Use perhaps even VPN technology in order to have the management console communicate with the firewall module. You might want to use tunneling, IPsec or whatever, if you have the corresponding license. And of course, for control connections, you should never ever use 127.0.0.1/non, because this does not make sure that the connections are only coming from localhost, but everybody can say I am localhost and will not have to authenticate himself when establishing control connections. Yeah, and what you finally want is probably more than one line of defense. We have seen installations that have like one firewall, or in general just one firewall with 16 or 20 interfaces, and this is the only point of defense. So if there's an implementation error in there, and we've been talking about configuration errors and implementation errors, and although we have been showing quite some things, this doesn't mean that firewall 1 is a bad firewall, because it just means that we up to now only had the time to look at firewall 1. So next year there might be the same things, just with other firewalls. So like we have seen before, we have seen that those attacks can be classified. So it's quite likely that some of the attacks also apply to other firewalls in slightly different ways perhaps, but they might even apply to other firewalls. Like we saw before, the FTP ozone thing. It was even worse, although we discovered it for firewall 1, it was even worse for Cisco PIX, for example. So it's not a sign that firewall 1 is bad. It has implementation errors, of course, but implementation errors are in almost any product, or in basically definitely any product. So we want more line of defense, because if you have 2 lines of defense, especially if you have 2 lines of defense constructed by different vendors, you have a certain chance that mistakes that one vendor makes are not repeated by the second vendor and the other way around. So that's a lesson that can be learned from what we've seen now. Use more lines of defense, especially if you use those lines of defense from different vendors. So, like I said before, we didn't even have to approach Checkpoint, but Checkpoint learned that we are giving a speech here, and they approached us 4 weeks before the whole thing here happened, and they cooperated very closely with us. They were pretty responsive, and we had a phone conference with their technical staff and so on. And we have learned that they have made available fixes for the problems shown today on www.checkpoint.com tech support. And yeah, we haven't had the chance to look at this, but at www.checkpoint.com tech support, the latest fixes can be downloaded. So this is the end of our presentation.
Wait. We forgot one thing. Buffer overflow.
The buffer overflow, yeah. Do we have a slide for that? No.
That's not really that cool.
No, it's just, yeah. Okay.
All right. So what I'm going to do is, there's some publicly available ports, even on the latest version, that allow you to run just a couple commands. And we were playing around with it, and we ran into a buffer overflow in one of the commands. Now, it's just like, what's that? Okay, it's just like, basically, it would be extremely difficult to exploit. What happens is it takes your input, it concatenates something to it, and then writes it over a variable in the stack, but right before the function exits, it checks one of its arguments. So there's no way you can overwrite the IP or anything important without the concatenated stuff messing up that argument, and it's checking if the argument is 0. So there's nothing you can really do. The only thing we came up with is you could overwrite the LSB of the saved base pointer with 0. But I played with that a while. On version 3, it was actually maybe you could do that with like a 20% chance of it working. But on version 4, you have to sanitize the stack a bit too much for it to be a plausible attack. But it does work on the latest version, and the only really thing you can do with it now is a denial of service on the firewall daemon. So I can show you that real quick. So you can see here, what happened is that function checked its arguments and it saw that they were messed up, and then it exited. It killed itself. Now what's cool is it says filter uninstalled, which would be nice, but it doesn't really uninstall it. So all you can really do, yeah, we were pretty happy when we saw that, but so all you can really do is kill the firewall daemon, which could be a pain.
Okay, but now we have finally come to the end of our presentation. I would like to thank you for your attention. Are there any questions? Yes, please. Yes, please. Wait, I'll just come to you with a microphone.
Jerry Springer style. Was SNMP by default on the firewall one?
Yeah, the question was whether SNMP was by default on. On the IP440, yeah, the SNMP daemon is running by default, and on Solaris it's normally running as well. That's why we were able to exploit it. And all we had to do is open the corresponding port on the firewall in order to access it, but it's normally running. Yeah, people don't harden their firewalls. Because it's nice, because then you can only, if you want to have the interfaces of the firewall, you just click on get, and it's nice to administer. That's why people have it running.
Hi, nice to meet you. Hi, how's it going?
Yeah, we run it as a honeypot system.
Thank you. Oh.
I thought
Oh yeah.